Okay, we're going to go a little bit deeper into this concept of power. Power is rejecting the null hypothesis when it was the right thing to do. It's getting it right. The person really did do the crime. Hey, what are the chances the jury's going to come back and convict them? It's making the right decision when the alternate hypothesis was correct. All right, kind of an industry standard for this is 80%. You would like, if the alternate hypothesis is correct, to sniff that out about 80% of the time. That would be the goal. Okay, if you had a 5% alpha situation. All right, what we're going to talk about today is what are some ways that you could increase power. Remember, power in number 67 was 53%. You've only got a 53% chance of getting an X bar that's going to cause you to reject the null hypothesis if we're supposed to reject the null hypothesis. What are some things that we could do that would get that up higher? All right, the first thing is to analyze the alpha level. I want you to think about this for a second. If you change the alpha level, what kind of a change in the alpha level would increase power? So everybody think about it. I want everybody to kind of have a prediction in your mind. Increasing it or decreasing it? Which one of those things would increase our chance of making the correct decision if the alternate hypothesis is correct? Skylar, what do you think? Increasing. So you're saying increasing the alpha level will increase power. Now there's two ways I want you to think about this. So give me your logic on that.
If you're increasing your alpha level.
So that if you're increasing your probability of a type 1 error,
then your bottom chart is moving to the right.
Oh, so you're going to move this thing. Okay.
Well, yeah. So if you're increasing.
So we're going to talk about this. Okay. So right now our alpha level is 1%. Okay. If this increases, so let's say it goes to 5 or 10%, this line is going to move to the right. So take a look at this now. Take a look at our graph down here. What happened to power when this alpha level got bigger? It got bigger, didn't it? Okay. All right, I thought you were going to tell the other way to think of this. Here's the other way you can think of this. When you increase alpha, you increase the probability of a type 1 error. What are you doing to the probability of a type 2 error? Decreasing. So if type 1 error goes up, type 2 error goes down, but if type 2 error goes down, what happens to power? It goes up. Right? These have to add up to 100%, right? So if type 2 error goes down, power must come up. So remember it any way you can, okay? From the pictures or play this game. But I agree, increasing the alpha level will increase power. Yeah.
So what's the practical application of this concept in statistics when you have to know the true mean?
Okay, we're going to talk about that in a second. We're going to talk about the true mean in a second. Okay, all right, number 2, sample size. How do you think, what can we do with sample size? In this problem it was 840. What could we do with sample size that you think would also increase power? Think about this for a second. Again, there's a couple of ways that you can describe this to me. I need you to kind of remember one of them. So, who had a candidate? What do you got? What do you think about sample size?
Increase it.
So you think that increasing, taking a sample bigger than 840 would increase power. Why?
Well, because then you'll be closer to the true mean.
So what are you saying? Kind of law of large numbers here? Is that what he's saying?
Yeah.
That if I take a bigger sample size, aren't those X bars going to get closer together?
So then, so it'll be, you'll have more confidence in saying that either rejecting.
I like what he's saying. Here's what he's saying. Look, if someone says that the real mean is 275, if I take a big sample size, a larger sample size, shouldn't I expect my X bar to be closer to the right answer? So yeah. Another way to look at this pictorially, if you take a larger sample size, what happens to all these X bars? Get closer together, right? So this picture, and this is kind of hard to see in this example, But this picture is going to get higher and skinnier over 270 over here. Power would grow in that situation. But the bottom line, bigger is better, right? Take a larger sample size, you got a better chance of doing the right thing. That makes sense, right? With me? All right, let's get to Zane's comment here a little bit. How does where the real mean is affect power? For example, right in this problem they said the true mean was 275, and that they said it was 275, but we actually know the real mean is 270. Tell me about this number. If this number was closer or further away from this, which one of those situations would increase power? Let me say this again. What if the 270 was closer? Or what if the 270 was like 250? Which one of those situations would increase power? Would you want the real mean to be closer to the 275 or further away from the 275 to increase power?
Closer to the 275?
Okay, so if the real mean was 273, you think that's going to give you a better chance to reject the 275. Why?
Well, if you just take the graphs, if you move the line over closer to...
Well, no, we're not moving any lines. What's going to be moving if we change the 270?
The whole graph.
This whole graph is going to be shifting one direction or the other, right? Kind of a shift is going to increase power.
If it goes further away.
So you think if the real mean was further away than 275, it would help with power. Why?
Because the further away from the null hypothesis you are, the less likely you're going to get a sample size of like closer to the null hypothesis.
That's perfect, man. Let me try to say what we said. Remember when I said some clown said that the true mean length of names is 5? Right? Somebody said that, right? And we know the real mean is far away, right? So when I go take my sample, isn't my X bar going to be really far away from what they said was true? So isn't it going to be easy for my X bar to disprove that? Because what they said was true was so far away. It's exactly what you were saying. So the further away what they say is true from what is really true from what they say is true increases power. Now let's look at this picture thing. Let's say this was a lot further away. So let's say it was 240. So this picture is going to be over here at 240, isn't it? And then look how much bigger power got. That stayed. This side is power, isn't it? The whole thing is going to be power. It's super easy to prove something wrong if what they're saying is crazy. Now, if what they say is true is really close to what we're trying, to what is really true, then you're going to get X bars that are going to be kind of close to both those two, and it's going to be harder to prove. Okay? Does that make sense? So, the further away the actual mean is from their hypothesis, the higher power is. Now, to answer your question, Zane, how do you use this in real life? What they do is they make up a true mean. And they say, okay, you know, someone says it's 275. What if it was 270? What if the real mean was 270? What are my chances of what are my chances of being able to get the right answer? Okay, so they kind of play games with what if the true mean was here. If the true mean was here, how big of a sample size would I need to take to get 80% power? You know what I'm saying? That's how they use it in real life. Because we don't ever know that, right? But they run different scenarios to figure out sample size or what we should set the alpha level to so that we get this 80%.
Is that how they get the standard deviation of the
No.
entire population also?
No.
They don't
See,
know that?
this is something we can't control. It is what it is. You know, and we're going to talk about this in a second. But this is just something they play with to go calculate different, whatever sample size or alpha level. Because these are two things you can control. Right? Going into a problem, you set the alpha level, you set the sample size. These are things you can't control, but they play with different means to see what kind of a sample size would be able to make the right decision. Power. All right, the last one, again, this isn't something you can control, but we should understand how it affects power. The population standard deviation. And we all know what that means, right? How far apart are the original numbers? Do you think these guys being really far apart would help power? Or do you think these guys being really far apart would hurt power? I guess I'm asking, do you want these guys to be close together, or do you want these guys to be far apart to help power? What do you guys think?
We don't want them to be far apart.
Okay, so we want them to be close together. Why?
Because, like we said, when the guy comes out with the number 5 as the letter names, well, it's more likely that he can be right if the deviations.
It's really good, man. You nailed it. What you guys take some pills today or something? I don't know. This is really good.
There's those smart pills you
I guess. You guys got some smart pills. Here's the thing. I'm going to try to explain a different way exactly what Eric said. Some clown says the true length of name is 5. What if I'm in a school where I got a bunch of tiny named people and a bunch of really big named people? So I get a big standard deviation, right? Now if I reach in here and take a sample, is there a good chance I could get the small name people and I could get a mean close to the 5? It's more possible, right? But what if every one of these people were 13 letters long? Right? Then when I take my sample, my X bar is going to be 13 letters long. Okay? So I agree. A lower population standard deviation does help power, but it's not something you control. Okay? So you're going to do a few problems tonight, doing problems, seeing how this concept plays out. But I need you to understand it either conceptually, okay, or draw a picture and move some stuff around just to double check to make sure you understand. Questions or comments? Okay.